Welcome to Ask and Learn.
Once again, welcome to a new problem. This time we have three components. We have natural gas. So natural gases, these are built from the earth, obviously. And then, of course, we have electric resistance. We have electric resistance. And then we also have a heat pump. So a heat pump produces a system. All of these three are considered systems of heat. And our goal in this particular problem is that we're looking for the system which is the most reversible. So we're looking for the most reversible system, meaning that if we have some heat and then we kind of like lose the heat, for some reason we can get back the heat. So there's a cycle, something that's cyclic. Which one is the most cyclic, the most reversible? If we think about these three, we get to see that first of all, let's look at the natural gas. We want to look at the natural gas. And when you think about the natural gas, is that its calorific value is high. And because of that, we're going to have high levels of heat produced by this system. So there's going to be high levels of heat produced by this system, and the levels of heat produced require efficient systems that regulate the heat. And so the problem with this is that large amounts of heat are lost to the surrounding. Large amounts of heat are lost to the surrounding. So this is called dissipation. We're losing large amounts of heat are lost to the surrounding. That's called dissipation. The temperature, high temperatures of natural gas systems lead to high levels of irreversibility. So we're losing the heat. There's a lot of dissipation. You can see. And there's no system to regulate that. So that's what we get when it comes to natural gases. And of course, this is a furnace. So it's a furnace, and therefore it burns fuel. And the system will have burners. It's going to have burners. It's going to have heat exchangers. It's also going to have a blower, so it has all of this. And the level of irreversibility is high based off of this system. So the level of irreversibility is high based off of the system. The other system we're looking at is obviously the electric resistance. We know, almost like when you think about bulbs with a filament, they do have electric resistance. And think about a filament that looks like that. There's electric current that flows in. This is your heat, which we call Q. This is your heat. And there's flow of current through the system. And outside, we're going to have outside temperature. This is going to be outside temperature. That's what we're looking at. And so in this particular problem is the electric resistance produces heat that is non-cyclic. So it produces heat that's non-cyclic, and therefore there is lost energy when the system performs electric work with dissipation. So this is the key, with dissipation of heat. And then we're going to say as a result, there are high levels of irreversibility. And then, of course, finally, we do have a heat pump, which is special in its own way. We have a heat pump which is special in its own way, and if you think about it, it follows the Carnot cycle. Okay, so we have a heat pump with a Carnot cycle, and this is a high temperature. And the heat pump is right here. This is your heat pump, and this high levels of heat, high heat levels against low heat levels. So the pump is able to cause low temperatures. This is outside low temperatures to flow to the to flow through work. So there's work performed by the pump, and it causes the heat to move from the lower levels at this point up until the higher levels. So there's some cycle going on over there. So we're going to say that heat pumps constitute central heating and cooling systems, central heating and cooling systems. With outside air used to cool the home in the summertime while the same heat from outside in the wintertime is pumped and heats up the home. And so there's almost like a reversible process. The heat pump moves air in and out. So the heat pump moves air in and out based on external seasonal conditions. So there's certain external seasonal conditions. For instance, in the summertime, heat is pumped from inside to outside. And so this is our conclusion, and you can see where we're going to end up with this. We're simply going to say that the heat pump is therefore the most reversible system, or you can say the least irreversible. They mean the same thing. The least irreversible system. So once again, we had three heat systems. And the first one was natural gas, and then electric resistance, and then the heat pump. The heat pump ended up being the most reversible or the least irreversible because it was able to take air from either low temperatures to high temperatures or high temperatures to low temperatures, depending on the seasons. The other two have super high calorific levels, especially natural gas, and it's least reversible. And when you have natural gas, you're producing a lot of energy, but then you can go in the opposite direction. The same applies to the electrical resistance, which relies on a coil like you've seen in this case. And so the electrical resistance produces heat that is not cyclic. There's a lot of dissipation going on. So it's ends up having high levels of irreversibility. Of course, the heat pump is the best when it comes to reversibility because we don't have a lot of dissipation other than the pump, working on the pump in a cyclic manner. So there's work going inside the pump. So hope you enjoy the problem. Feel free to send any questions or comments, and have a wonderful day.